This is number 26 on page 289. Again, this is a raft. So unlike the frog problem, this is a raft, and it gives us the density of the raft. It gives us the area of the raft, at least this face here, and then it gives us the total volume of the raft. And the question they have, if you put it in water, how deep is the bottom of the raft below water? Just let me read the whole thing. A raft is constructed of wood having a density of 600.0 kilograms per meters cubed. I wrote that down already. The surface area of the bottom of the raft is 5.7 meters squared, and the volume of the raft is 0.60 meters cubed. When the raft is placed in fresh water having a density of 1,000, basically 1.0 times 10 to the third kilograms per meters cubed, how deep is the bottom of the raft below water level? So basically, we want to know, when we put this in water, so let's pretend this is water here that goes all the way around, right? We want to know how deep is it in the water. So we're wanting to know this distance right here from here to there. We want to know what is H? That's what we want to know. So how are we going to approach this? Well, this is a buoyancy problem. So it's floating. What do we know about the forces? Well, we know the buoyant force is pointing up, right? That's the water. It's not a very good buoyant force. And we know that the force of gravity or the weight is pointing down, which would be mass of the raft times G. All right. So basically we're going to put an equation together that says FB equals mass of the raft times G. So the question is, how do we find all this? So let's write down what equations we know. Again, we know buoyancy is the density of the fluid, which is water, so we know that, times the volume of the fluid displaced. We'll find out in just a minute. That's kind of sort of what we're looking for. Times G, that's all buoyancy, and that is going to equal mass of the raft times G. All right, now you can already see that our gravities are going to divide out. So we can go ahead and divide those out. We won't need to add those since they're on both sides. Now we do not have the mass of the raft, but if you remember the equation, density is mass divided by volume. And so mass equals density times volume, and it just so happens we have both of those numbers given to us in the problem. So I'm going to rewrite this whole thing out, and it's going to be density of water times the volume of the water displaced equals density of the raft. Now that's different from the water. That's the 600 kilograms per meters cubed times volume of the raft, which we know that's 0.6 meters cubed. All right, so let's put our numbers in. 1,000 kilograms per meters cubed times volume of the fluid displaced, which we don't know, has to equal 600 kilograms per meters cubed times volume of the raft, which is 0.6, oops, 0.60 meters cubed. All right, so we're looking for volume. So 600 times 0.6 gives me 360 on this side. Let's make this a little bigger. So I got 360 kilograms on this side. And that's going to equal 1,000 times V. So if I divide both sides by 1,000 kilograms per meters cubed, that's going to give me the volume of the water displaced, which is also the volume of the raft underwater, because the volume of the raft underwater is the amount of water displaced, or the volume of the water displaced. And that's going to give me 0.360 meters cubed. Now that's not my answer yet because they asked for H. What is volume? Well, if you remember from math, volume is area times height. And so we have 0.360 meters cubed equals, do we know area? Sure. Sure, we know area. It gave it to us. It's 5.7. 5.7 meters squared times H. So the only thing we don't know is H there. H equals, and so we're going to take 0.36 divided by 5.7 meters squared, and that's going to give me about 6 centimeters, looks like. 6.3 centimeters. I'll write it out here. I'll write it as meters. 0.063 meters, or 6.3 centimeters underwater. That's how much of the raft will be underwater. So this little number here is 6.3 centimeters. That's how you do that problem.